Welcome everybody back to our 100th anniversary distinguished alumni guest speakers. So today's speaker is John Tobin, and John got his bachelor's degree from Illinois in 2006, was one of our Wyatt Award winners, and went on to the University of Michigan where he got his PhD in 2011. He was a Hubble Fellow and a Venny Fellow in the Netherlands for a couple of years, and then an assistant professor at the University of Oklahoma for a couple of years before becoming an associate scientist at NRAO in Charlottesville in 2018. John works on star and planet formation, and today he's going to tell us about disks, multiplicity, and stellar masses of low and intermediate mass protostars in Orion.
All right, thank you very much for the introduction, and I'm very pleased to have been invited to give a colloquium as part of the 100th anniversary series. Unfortunately, we're not doing things in person yet, but hopefully in the near future I'll get a chance to visit the campus again and reconnect with everyone. But I'm glad to be able to tell you about what I've been up to over the past 15 years since I graduated. So just first briefly to talk a little bit about my time at Illinois. So I was only there 3 years, 2003 to 2006. I was part of the UIAS, the Astronomical Society, and so I did a lot of personal observing on the 12-inch on campus, and had some rudimentary attempts at astrophotography with using film back then, even though it wasn't that long ago. Still, digital SLRs weren't quite a thing yet, but I got some nice images of the moon, Saturn. This is part of the double cluster in Perseus. And at the same time, while I was here having fun with the telescopes, I managed to meet two great mentors in Brian Fields and Leslie Looney, whom both happened to be the first astronomy classes that I took at U of I, and I think they played a large role in both guiding my the research arc that I've taken in my career, and really cementing my passion for astronomy and helping me focus that into fruitful directions. And so also had Leslie gave me the opportunity to go out to Kitt Peak with his graduate student Shia, and so you can tell that this was a little while ago, given the monitor technology being used, and the telescope was driven by even older computers, which was quite interesting to see, as you can see with these monitors that are on the upper rack here, driven by some sort of very old archaic computer system. But had a lot of good time, good sleep-deprived nights out at Kitt Peak with Shia, took a lot of data, and had a couple of pretty pictures that we took. This one is the Sombrero Galaxy, and this was incidentally the first near-infrared image I ever reduced. But even with just a couple minutes on source, you can see the bulge and the disk nicely, and you can even see the dark lanes of the molecular clouds in the galaxy. Then also in my last year and a half or so, we did a lot of science. So with Leslie and Brian, we worked on trying to figure out how close the Protostellar Nebula was to a supernova, based on how much short-lived radioactive nuclides that we have observed on Earth relative to how much they're expected to be produced in supernovae. And then did work on a couple of star-forming regions, L1448, which was my first author paper with Leslie, and I'll come back to this region later in the talk. Then also on L1157, and I sort of arrived at a very interesting time because Spitzer had just launched, and we had all of this beautiful data coming in from Spitzer, and that's where these two images come from. These were 3-color images made from the IRAC data, and so I had a lot of fun combing through all the data that were available on starform regions and making pretty pictures like these. Now diving into the main heart of my talk. As part of my duties at the National Radio Astronomy Observatory, I am the project scientist of the Science Ready Data Products Initiative. So I'll tell you a few things about things that are going on at NRAO before I get into the science. So what we want to try to do for both ALMA and the VLA is provide users with higher quality data products, higher value data products, and overall make the data easier to use and work with so that we can spend more time on science and less time on data reduction. So as part of this, we've developed a new NRAO archive interface that serves both the raw data and images. We now have the capability for users to download calibrated visibility data for the VLA and ALMA, which before this was a manual process where you either calibrate it yourself or rerun the calibration on your own computer. And then we have an imaging service that we call ALMA User Defined Imaging, where you can create new ALMA data cubes and continuum images with a simplified interface. And then the images are run on NRAO computing, and when it's done, you'll get your image back. And to go along with this, we've instituted a quality assurance process for VLA data, such that the data that have gone through the VLA pipeline that you get delivered to you should be ready to image. And we're providing this for all VLA continuum data that are at C-band and higher frequency. And so as of recently, we've been delivering about 40% of our data as the Science Ready Data product. And now one of our newest features is that you can view all the images from the VLA Sky Survey, which is an all-sky S-band survey, within the NRAO archive using the CARTA image viewer. So you can look at a lot of data without having to download anything. And if you don't like it, you haven't taken up your own disk space and you're not cluttering your own system. And so if you want to access any of these capabilities, you visit data.nrao.edu. And so one of the motivating factors, in addition to serving our community, is that we think that providing science-ready data products is going to be essential for community acceptance of the next generation of radio facilities, which is a nice segue to one of the other projects that's going on, which is the next generation VLA. And I guess we will find out the outcome of the decadal survey later this week and see how it fared, which will probably play a large role in the future direction of this project. But the NGVLA is meant to complement ALMA and complement the eventual square kilometer array. And so it will sort of bridge the gap between the low frequencies that the SKA is going to probe and the high frequencies that ALMA probes. And this is meant to be a completely new instrument, but it's going to be centered at the footprint of the original VLA and go from about 1.2 gigahertz to 1.6 to about 100 gigahertz. So essentially from the 21 centimeter line all the way up to the CO 1-0 line, we'll be able to get, will be observable with the next gen VLA. And the resolution of it is going to be about 10 times what the current VLA is and have about 10 times the sensitivity. And so where will it be? Well, I've already said it'll be centered on the current VLA footprint, which you see here, which is about 50 miles west of Socorro, New Mexico, southwest of Albuquerque. But there's going to be a lot more stations over a lot longer baselines. And so you can see that spread throughout the state of New Mexico with stations into Arizona and Texas. And it's going to have a very dense inner core for imaging extended low surface brightness objects. The outer part, which is still in the footprint of the current VLA, is going to have a spiral pattern. But going out to longer baselines, it gets a bit more irregular, and it's a lot of that's determined by available infrastructure such as power and fiber optics. But VLBI is also built into the NGVLA, and so the whole thing is one instrument, one interconnected instrument. So it's so there's not going to be a separate VLBA, VLA anymore. It's just all going to be the next gen VLA. And so we're hopeful that with the community support that has been built up behind the project, that it will have a favorable outcome. And the idea is that this would be producing early science in the late 2020s with full operations in the mid 2030s. Now segueing into my science. So I have very extensive use of the NRAO facilities, and I'm concentrating on sort of these main questions that I'll talk about here, which are the physical properties of newborn disks, when planet formation begins, and how often stars are forming as multiple systems. So first off, just to give everyone an orientation to what star formation in a molecular cloud looks like, at least from one wavelength. This is a Spitzer image of the Orion Nebula. So you see the Orion Nebula down here, and the trapezium cluster is the very bright spot down here. But one of the most intriguing regions is the region that isn't really lit up at infrared wavelengths, and you see a lot of dark material here with maybe a few little points of light on it. But if you look at this with a millimeter or submillimeter telescope, you'll see that this dark material is actually glowing when you look at it in thermal emission. So this is black body emission that's coming from the cold, dusty material that is making up the molecular cloud. And within this dense, dusty materials where the stars will be born. And one thing you'll notice looking at this image is that there's a lot of surface brightness fluctuations along these filamentary features. And you can pick these all out, and we tend to call these dense cores. And these dense cores are going to be the sites of star formation. So these cores are, when they become gravitationally bound, they'll collapse under their own gravity. And to get a sketch of what's going on inside one of these, this is an artist's conception of what one might look like, where inside one of these dense cores, they're about 1/10 of a parsec in diameter. You have an infalling envelope. So if it's collapsing under its own gravity, we call this extended material the envelope. And then due to conservation of angular momentum during the collapse process, a disk will form around the nascent protostar. And the interaction of that protostar and disk is going to drive a bipolar outflow, which in this artist's conception has blown the tops off of the clouds and creates a cavity, which is how we're able to see a lot of these protostars in the infrared light. And these disks can also be the birthplaces of planets. They can be the birthplaces of binary star systems, like I show in this zoom in, where within the inner 100 AU within your disk, if it's gravitationally unstable, it may fragment and form more than one star within its disk. And so a lot of what we need is the ability to peer through this dense, dusty material to see into these newborn disks. And so we require resolution on the order of tens of AUs. And the only way to really do that and be able to see what's hiding inside these dense cores is to use a submillimeter interferometry. And so first, we'll see what interferometry tells us about the properties of the newborn disks. And so a couple of surveys that I've been leading to study newborn disks and multiple star formation are called the Damme Surveys, the VLA and ALMA Nascent Disk and Multiplicity Survey. We've done 2 surveys now. We did one of the nearby Perseus star forming region, where we looked at 92 protostars with about 21 AU spatial resolution. And then following that survey, we did a survey of 330 protostars in Orion. Most of the 330 were done with ALMA, and then 150 out of that 330 were done with the VLA. And again, we had about 20 to 50 AU of spatial resolution. And so we were able to really peer it into these dense cores and with enough resolution to see disks if they're large enough and resolve them. And so I'll talk mainly about the Orion survey today, but a lot of great work was also done on the Perseus survey. So this is an overview of the entire Orion region. So what I showed a couple of slides back, that was just the Orion Nebula, which was sort of right down here, just a little small portion of the region. But we looked at protostars throughout the entire Orion molecular cloud complex. And so each of these little crosshairs is a protostar. The blue ones are the youngest ones. The cyan ones are the most evolved ones, and the magenta ones are in between. And this is just an overview of a very small sliver of our sample of what we see towards the protostellar disks when we look at these protostars with a resolution of about 20 AU. And so these aren't any protostars in particular. This is just a random sampling, but we see a wide variety of structures. So we see some of them are very compact, some of them are very big and extended. And I apologize, I forgot to point out the reference, but the scale bar down here is 100 AU. So the unresolved things, the things that look like our beam down here, they are less than about 20 AU in diameter, but anything that is the size of the scale bar or bigger is quite well resolved. And so we see a variety of structure in these disks around very young protostars. And for the first time using these survey data, we're able to get a complete picture of what all of the masses and all of the radii look like towards disks in a young star forming region. And so the question has sort of evolved. It used about 10 years ago, the question was, do disks actually form very early on in the star formation process? But now with the survey data, we're able to explore questions about what are disks like, what do their properties depend on? And this is due to the power of these large demographic surveys that we can do now, largely enabled by ALMA and the expanded very large array. So what we're able to do is we now sort of know what a typical disk is like in each stage of protostellar evolution. And it was a little different than what we thought it would be, but that's okay because that's the way science goes. So for the youngest protostars, we found that the disks actually tend to be the largest at the earliest stage. So we were finding a median disk radius of about 54 AU, and they were about a median mass of about 38 Earth masses. And then class 1 protostars have a median mass of, or median radius of 35 AU and a median mass of about 13 Earth masses. And the flat spectrum protostars, which are in between the class 1 phase and becoming just a bare protoplanetary disk, they are actually about the same. So we had expected that disks might grow in size going from the youngest to the more evolved, because as material is falling in toward the disk, it is expected to come in with higher angular momentum because it initially started falling in at a larger radius. But that prediction isn't really bearing out, and it seems that the disk radii seem to be either slightly contracting or more or less constant with time as the protostars evolve. And I don't show plots of this here, but I'll add that there's a ton of scatter within the disk radii as a function of proxies for age and luminosity. So there's not really any clear-cut trends in the disks that we can pull out from the data at present. There have been some complementary studies that have been taken on by independent groups. One of them was trying to look for correlations between the disk radii, magnetic fields, velocity gradients, and turbulence, and they found that nothing seemed to be correlated with the radii we were measuring for the disks. And so, and that led them to suggest that perhaps it's non-ideal magnetohydrodynamics is what is ultimately governing the properties of these young disks. Because if you have strong magnetic fields, the angular momentum is not conserved as you're falling in, and you can actually slow down your rotation significantly. But then with high enough density, non-ideal MHD can dissipate the magnetic flux and enable the disks to form. And so that can act somewhat independently of the properties of the star-forming clouds itself. And one note of caution with these quantities is that they are observationally derived just from the data itself, measuring the flux and fitting Gaussians to the observed images. But how do you do better than that? Well, one obvious direction is forward modeling of the observations. And that's an area that that my former postdoc has been pushing on, Patrick Sheehan. And he's been trying to overcome some of the limitations that we have of the observables. So if you have a parametric density distribution, so if you have some sort of model for what you think the dust distribution around a protostar should look like, which there are several analytic models to choose from. So you have a disk, you have an envelope, and an outflow cavity that you represent as with power law density profiles. And then you perform a radii of equilibrium calculation that will give you the temperature of all this dusty material. And then you can ray trace the density and temperature structure to produce synthetic observations. So in our case, synthetic spectral energy distributions and millimeter visibility data. And you can couple this with Markov chain Monte Carlo sampling or nested sampling and try to perform very rigorous fits to the data. And so that enables you to make plots like these where you're essentially plotting every parameter against every other parameter, and you can use these posterior distributions in order to get an estimate of the uncertainties on your derived values. And so historically, this has been done sort of with by eye fitting, where you tune parameters by hand or use poorly sampled grids to try to find a best fit model. But with the increase in computational capabilities, you're able to perform much more rigorous fitting and get a much better idea of how well your model fits to your data and what your parameters are. But of course, we're still limited by how well the data are represented by these models. So the models are still simplistic in that they're axisymmetric density distributions and so forth. But going to more complicated models like 3D density structures doesn't necessarily provide you new information. And so just to give an example of how well this modeling can work on the data, on the left, I'm showing you a visibility amplitude versus UV distance. At the middle is an image with the model contours overlaid. And then on the right is a spectral energy distribution, so flux versus wavelength. And the model is the solid line here, and then the data are the points, and there's spectrum in here that's maybe a little hard to make out. But with this type of fitting, we're able to match the data quite well in most instances. And we can decouple the envelope from the disk towards the protostar. So by the nature of the Fourier transform, because big things are going to be at short UV distances in the Fourier plane, and then small things are at large UV distances. And so we can see the envelope here has lots of flux at very short UV distances because it's very big and very massive. Whereas the disk has a lot more flux at long UV distances because it's very compact and it has overall less mass. And so these two examples sort of show you the extremes of what you can get, where you can get something that has a very, very massive disk where the envelope and disk sort of are competing in UV space. Or you can have a case like this where the envelope is pretty dominant for most UV distances until you get to the very longest baselines, where only there do you see evidence of a very compact component that we could describe as the disk. And so by doing this fitting, we're able to get much closer to the data itself and perhaps derive more realistic parameters for the disk radii and disk masses. And so Patrick Sheehan has done this for about 97 disks, and he's finding somewhat different quantities. And so for the class 0 disks, the median radii are 36 AU, but he's still finding that the class 1 and flat spectrum disk radii are a little bit smaller, or perhaps they're a little bit smaller. So maybe there's a decline with age still. But a big difference is in the disk masses that you get out of the radiative transfer modeling. And so he's getting lower masses for the younger sources, and then the most evolved sources have a bit higher mass. And so these differences result from optical depth of the dust continuum emission, as well as the dust opacities that are assumed in the modeling and the temperature of the dust. So our simplistic derivation of the disk masses assumed optically thin dust emission, a uniform disk temperature, and so forth. But with the radiative transfer modeling, you put a lot more physics into the synthetic observations, and you can get out a more realistic result. So in these plots, what's being shown is the mass that we got from the observational fitting versus the mass that you get out of the radiative transfer modeling. And the dashed line in each of these plots is the 1-to-1 line. And so you can see that up here at high disk masses, we're not doing too bad. So these large disk masses are getting approximately the same as what the radiative transfer modeling gets you. But it's really these very low disk masses where we're substantially different by perhaps close to an order of magnitude. And where you have 1 Earth mass from radiative transfer, and we were estimating 10 Earth masses from just the flux density alone. And a lot of that is simply due to the dust optical depth and the dust temperature, because if these disks are very compact, you're not going to get as much flux out. And if you underestimate the temperature, you can vastly overestimate the mass. And then coming over to this plot, this is a plot of the disk radius from observations versus radiative transfer modeling. Again, there's a bit of a difference, but there's a lot more scatter in the disk radii, and so the correlation isn't quite as tight as it is with mass. But again, for the larger disks, we tend to do better than we do with the smaller disks, and part of that is just because of our resolution limitations. But you can see on this plot, this is the flux density that you get out. So the flux density from just measuring it off of the images versus doing radiated transfer modeling is very much the same. So for different flux densities, you can end up with vastly different masses and different radii. And so I've told you here sort of two contradictory results where I told you this is what we measure the disk masses to be. And then I tell you that it's something completely different here. And you might be wondering, well, I've told you two very different things, which is correct. The short answer is we're not actually sure which is correct yet. We think that it's possible that this method might be more correct, just due to the fact that we're putting in more realistic, we're trying to forward model the observations, and we're trying to realistically reproduce the observations with a model. But one of the details here is this dust mass opacity, which we don't have a great constraint on. And so this is how you convert your dust emission into a mass. And there are a lot of different models out there for what it should be, but it fundamentally depends on both the grain mineralogy, the ice content, the size distribution of the particles, and whether those particles are solid spheres or whether they are fluffy aggregates. So a lot is unknown about the dust, and until we really know more about the dust, it is hard to really say which of these masses are correct. But for the remainder of the talk, I'm going to mainly discuss the observationally derived masses to compare with other observationally derived masses. Okay, and so now that we've established disks are forming early, we know a lot about these young forming disks now, and we actually want to understand, when does planet formation begin? And so here I'm plotting cumulative distributions of so on this axis goes from 0 to 1 is the fraction of disks with a certain dust mass, and then on this axis is the dust mass itself. And so I'm plotting on here the Orion protostars, which are located here in these shaded curves that are furthest to the right with the highest masses. And then these other curves that are plotted here, these are more evolved star forming regions, and these are disks that are evolved beyond the protostar phase and have quite a bit less mass than what are typically referred to as protoplanetary disks. But are these protoplanetary, but one of the problems that has been encountered is whether these protoplanetary disks actually have enough mass to create planets in the planets that we are observing. And so now I'm going to draw a few vertical lines here. This is the minimum mass solar nebula. And so any disk to the right of this vertical line doesn't have enough mass to reproduce the minimum mass solar nebula. And so the minimum mass solar nebula is a key figure of merit for being able to produce all of the planets in our own solar system. And so most of these protoplanetary disks don't have enough mass to reproduce the minimum mass solar nebula, but more protostellar disks do. But even though the protostellar disks, there aren't too many of them to the right, it's less than the median. But if now you get into the ability to make a giant planet core, which you need something about 5 to 10 Earth masses, and so that's one giant planet core. And so for these particular disks that intersect with the vertical line, you'd have to take all that dust mass in that disk and somehow get it into a single giant planet core to make one core within these disks. So many of the protoplanetary disks are going to have difficulty making just a single giant planet core, whereas the majority of the protostellar disks have enough mass to make a giant planet core. And if you want to form Earth-like planets or super Earths and the like, now you're sort of getting into the median of the protoplanetary disks, but almost all of the protostellar disks have enough mass to form the core of Earth-like planets. So this is a bit of a conundrum, but any way you look at it, evolution seems to be driving quickly within several million years. So these more evolved protoplanetary disks are a couple million years older than the protostars that I'm showing up here. They quickly evolved to have lower mass, and the question is, what's happening to this mass? Well, some of it gets accreted, some of it might be getting converted into planetesimals already. But the question is this observational evolution in the disk masses, is this real, or is the dust mass, is the dust just being converted into larger solids that are emit less efficiently, and then we're underestimating the masses? This sort of goes back to the question of radiative transfer. Are the masses the same, but the dust properties changing, or are the dust properties staying relatively the same and it's the mass that is changing? I think that's a very important question that is being worked on right now by many different groups from multiple directions.
John, could you remind us what sizes of dust grains are you sensitive to?
Oh, so these are observations at about a wavelength of 1 millimeter. So we're going to be most sensitive to things that are about a millimeter in size. But if you have smaller dust grains and you just have a lot of them, you can be sensitive to those smaller grains as well, but you need a lot more dust column density to detect it. So generally the rule of thumb is that you're probing dust that's approximately the same wavelength as your observation.
Got it, thanks.
Yep. So whether or not this is mass evolution or dust evolution, well, we think this is probably pointing to planet formation beginning in the protostellar phase, just because you need this large mass budget in order to form the planets that you see. And is there evidence for this? Well, there is evidence for some substructures in protostellar disks already. So these are a few examples out of the survey in Orion where the disks do not have smooth structure, where you see large rings with cavities surrounding an inner disk. And so we see this in, this was a very small fraction of our survey, but with our sensitivity, it was a snapshot survey looking at a lot of sources. We didn't have a lot of sensitivity to structures like this, and so we were sort of surprised to see such a large number of disks that are structured in just our rather low sensitivity observations. However, we can't definitively say, yes, this is planet formation in protostellar disks, because this could also be companion protostars forming and sweeping out a large cavity in dust as well. More work needs to be done to see whether this is a binary star or whether it's due to planets. But there's Patrick Sheehan is following up these disks with higher fidelity observations, and most importantly, observations of the gas emission lines that could be coming from these, coming from inside the cavities that we see in the dust emission. And so kind of my takeaway point here is that what we really want to know is, are these things that we call protoplanetary disks, which these are the disks that are observed by the ALMA D-sharp large program that saw structure everywhere. Are these protoplanetary disks really post-planetary, or are these simply protoplanet hosting? Because we think that in order for a lot of this planet formation to happen, it has to start early. In order for all of these substructures to be so well established by the protoplanetary disk phase. All right, now changing gears slightly, I'm going to change over to multiplicity and how often protostars are forming as part of multiple systems in the last few minutes. So multiple star formation has been known to be quite important, and a large fraction of the main sequence stars that we see in the sky are going to be part of a multiple system. And so understanding star formation also means understanding binary star formation, because half of the sun-like stars are in multiple systems, and if you go to higher mass stars, almost all of them are multiple. And even the low mass stars, they are less frequently part of multiple systems, but it's still a non-insignificant fraction of them. And so for the solar type stars, you see that they have a distribution of separations in the solar, at least in the nearby solar neighborhood, where their median separation is about 50 AU. So this is a histogram of all of the field solar type stars. On the bottom is the log of the orbital period. On the top is that orbital period converted to a separation in AU. And so they approximately have a peak at 50 AU. The lower mass stars, the M stars, peak at a bit lower at about 20 AU. But for a long time, protostellar multiplicity has only been examined for this really narrow range of multiplicity, roughly 500 to 1,000 AU. And this was driven, and this was mainly limitation of the observations, that we couldn't look for things that were closer. And so we were totally blind to the peak of the field solar type star multiplicity or field solar type star separation distribution. But at the same time, most protostars in this range, they were being found to be multiple. And so there were a lot of claims about how everything was a multiple and everything formed as a multiple. But some of these studies were based on small samples, and so there was a lot of bias towards favorite sources and bright sources, which were what you could observe with the interferometers at the time. But the surveys that I've been leading have greatly expanded the parameter space probe. So now, rather than going from 500 AU to 10,000 AU, we can go from about 20 AU out to 10,000 AU. So we've really opened up the range of parameter space we can sample towards the close multiples. And so now we can resolve the peak of the field solar type star separation distribution, but for protostars themselves. And the way we think multiples form is probably due to a combination of physical mechanisms. One of them is disk fragmentation for gravitational instability, where the mass of the disk causes it to fragment and form another stellar companion within the disk. And so to grow that companion, you need to have replenishment from that disk, and so it has to form during the protostar phase. Or you can have turbulent fragmentation, where the molecular cloud itself causes multiple density peaks that can collapse and form into protostars on their own. And then they can subsequently migrate around. Some might migrate in, some might migrate away. And so the molecular cloud itself will play a large role in when and where multiple stars can form. And so just to give you a glimpse of a few observations of multiples. And so we're using the same data that we used in the study of the disks, but now we're looking at the things that were that had lots of sources close together. So this top image on the left are the ALMA data, and on the right are the VLA data at about a factor of 10 longer wavelength. And so the ALMA data can tend to be optically thick towards some sources, and so we don't always see an indication of further multiplicity, like in this source here, where I have two crosses marked here, which mark the multiple system, which mark two components of the multiple system, but the ALMA data only show one peak here. But when we look at it with the VLA, we can tune a resolution a bit further, and at the longer wavelength, the dust is more transparent. A second peak is revealed that is embedded within this larger structure that ALMA is more sensitive to. And so we see that rather than being a binary system, this is actually a triple system. And then there's a couple of other examples of multiples here. That this one's also a triple, where you have a close companion to this source, and then a wider companion further away. And then this source is an interesting one. This is HH1 MMS. So this is the driving source of the first Herbig-Haro object, which are shock features associated with outflows from protostars. But we resolved a companion star right next to the main source here. And then this extension that you see that's orthogonal to the major axis of the ALMA data, this is free emission that's coming from the jet launched by the protostar. So we really, to fully characterize the multiplicity of the protostars, we needed the data from both VLA and ALMA, because they complement each other. They don't show exactly the same thing, and we don't learn everything with just one wavelength. We really need the long wavelengths to see further into these protostars.
So John, this is very cool. Can you tell that these multiple systems are gravitationally bound?
Oh, that
do you have enough information to know that?
That is a great question. We do not. That's one of the things we're working on for the ones in Orion right now. We think that these close multiples, so the ones I'm showing here, I mean, I forgot to mention the scale bar. These are all within a couple hundred AU of each other. These ones seem like they are likely gravitationally bound, but what we need are the velocities of each of these. Well, we can only get the line of sight velocity at present, but we can get the velocities of each component to see if they're consistent with being at least bound by the radial velocities. That's a question I'll try to come back to for the ones that we see that are more widely separated, because we think certainly not all of those are bound, and some of those are going to they might be a binary now, or they might appear as a multiple now, but then later on they will no longer be a multiple.
Yeah, very cool.
Yeah, so the way we study this in sort of a ensemble manner is that we use an algorithm that is like a nearest neighbor mechanism to try to link up these companions spatially. It's an iterative process where we sort of start from the small separations and search for progressively more distant companions. And so in this example, we have 4 sources, A, B, C, and D. The sizes of the circles doesn't really matter in this case. But when we're searching for companions, the first one we'll find is A is companion to B, and then we then consider this to be one system, AB, and then we use its average position as a proxy for the center of mass. Then we continue searching further out, and we'll identify that C and D are possibly related to each other, and so we'll link them together with an average position of those 2 sources. And then searching further out, we can link together both the AB system and the CD system into one entire quadruple system with a position defined by the center of mass. And so because of the limited information we have, we don't have radial velocities for many of these. We certainly cannot get optical radial velocities because of how embedded they are, but we can use molecular lines. But at present, we're solely analyzing the spatial associations of the systems. But we try to account for the possibility of contamination of other unassociated YSOs using a probabilistic method. And so I'll show you a plot with the possible contamination taken into account in one more slide. And so what I'm showing you here is the multiplicity fraction versus protostellar class. So class 0, the youngest being over here, and flat spectrum, the oldest over here. And then in this plot, this is the companion fraction. And so this includes higher order. This will include an additional counting for the higher order systems. So, and Then the field solar type stars are represented by the horizontal line with the error bars drawn as the dotted lines. And so what you can see is that really it's only the class zeros, the youngest protostars, that differ strongly in terms of their multiplicity fraction and companion fraction with respect to field solar type stars. But the caveat here is that this is only giving you a measure of how many multiples are there, not where we're finding those multiples. And so we also analyzed the distribution of separations, which, and so now I'm plotting you the frequency or the fraction of companions in bins along divided into separation. And so these histograms that you can see that we sort of have two peaks in this plot here, one around 100 AU, and then one again out beyond 1000 AU. And then the separation distribution of field solar type stars is drawn as this dotted curve. And so this separation distribution that we observe is found to be inconsistent with the field solar type stars, and it's also inconsistent with a log flat distribution. So it seems like this bimodal structure is at least might be statistically robust. And you'll notice that I have two things labeled here. These sort of light gray bars, these are not contamination corrected, whereas the dark gray bars are corrected for contamination. So when you start getting out beyond 1000 AU, we're much more likely to pick up unassociated young stars that might be foreground or background that have a disk around them, and we can see them at millimeter wavelengths. And so we've tried to account for those based on the measured YSO surface density around all of our targets that have been calculated from infrared measurements. And so as you can see, it doesn't really affect our statistics too much unless we're underestimating how much contamination we might have. But the more evolved protostars do not have such a large bump out at wide separations. This bump at the large separations is really driven by the class 0 protostars. So that's where we sort of see this strongest double peak ray of a bunch of companions piled up just under 100 AU and then a bunch beyond 1000 AU. The more evolved protostars don't have the same structure in their separation distributions. And so what we think is the cause of this is those two different mechanisms of formation I talked about. We think disk fragmentation might be happening here, where below about 300 AU. And then we think turbulent fragmentation is happening out here beyond 1000 AU primarily. And you can get some of these ones that formed out beyond 1000 AU. Some can migrate in and contribute to the smaller scale, and contribute to the more compact multiples. But we think that is probably less than 50% based on comparisons to simulations, these by Lee et al. 2019.
John,
now,
you should probably wrap it up soon.
Yep, sure. Yeah, and so now you might say, do we have evidence for disk fragmentation? I would say we are starting to get more evidence of it, but we at least have many systems that could be candidates for, or a few systems that could be candidates for disk fragmentation happening right now. And so this is an image from the VLA where we saw 3 systems or 3 compact point sources and maybe some diffuse emission in the background, but couldn't say too much about that. But ALMA at 1 millimeter saw this nice organized disk around these 3 sources, with what we used to think was the main source, the brightest one here at in the outer disk. And then we got an even sharper image of this one more recently from a paper that my grad student just published. And so we think that this is one of these poster children for for disk fragmentation, because it has a very massive disk. It has multiple clumps that formed in this disk, And I don't show the velocities here, but this is undergoing capillary rotation. So everything holds together for this to be a fragmenting system. And incidentally, this was the system that I showed in one of my initial slides. It's this little guy right here that I looked at as part of my first paper, working with Leslie. And then we have another guy that I showed in my first slide, L1157 here, where we zoom way in, going from 10,000 AU down to about 36 AU, where we're again finding a 17 AU binary, and that's work in prep. So the deeper you look, the more binaries we find. And with that, I think I will wrap it up. But one of the, this is my summary slide, but I'll say some of the things that we're moving on to next are measuring more protostar masses to try to get a better handle on disk stability. And we're trying to now resolve substructures in protostellar disks to try and get a better answer to the question of when do these substructures form and do they really reflect planet formation? And thank you very much.
Thanks, John. We already have a question from Telemachus. Telemachus, you want to ask your question?
Oh, okay. Well, I guess.
Sorry, I put it in the chat box. The question is, you use the term turbulent fragmentation. Do you mean that gravity is not playing a role in that process?
Okay, yeah, I think I heard that. Yeah, so no, I'm not meaning that gravity is not playing a role, but in the turbulent fragmentation, the turbulence is creating these creating the seeds for gravitational collapse. So the turbulence will form, the gas sort of sloshes together, and you'll create high density peaks in the molecular clouds, and so it forms the seeds of these dense cores. And then if these turbulent fluctuations have enough mass to be gravitationally bound, then they can collapse under their own gravity. And so the turbulence provides the seeds for the dense core formation, and then gravity can take over. And so it's not the case that gravity doesn't matter. The turbulent fragmentation just helps gravity along.
So they are all gravitationally bound then, or they can't go, as simulations of turbulence show that is often the case.
Also, so the simulations I'm referring to, this is like Matthew Bates simulations, Stella Offner's. They will within the simulation, that turbulence will create. You'll have local increases in the volume density, and then that high density can collapse under its own gravity.
Yes. Do we have any other questions? Yes, Brian.
Yeah, so thanks, John. That was a really interesting talk. So you've spent your time well in 15 years. At the very beginning, you had this beautiful image where you showed in sort of the big picture, it looked like a lot of these sources were all aligned on a filament. Is there any of their properties that correlate with their position on the filament? Like, do they know that they live in this filamentary structure?
Yeah, that's a good question. So yeah, I think it's this image you're referring to.
Yeah, that's the one.
So we've looked in. That's been looked into a bit. So I haven't looked into this with my sample yet. But there was this complementary study that I referred to that was done by Yen 2021, where they were trying to look at the correlations within the larger scale molecular cloud, and they didn't seem to find anything, at least coupled with archival measurements of magnetic fields or the velocities of these cores. And another thing we had looked into previously was with another colleague was up here in this very tip of Orion, we were trying to look at the position angles of the resolved disks to see if any of them were aligned or anti-aligned with filaments, but it seemed like it was a bit random. We didn't see any preferential alignment, so they don't seem to really know when the protostars form and their disks form. They don't always seem to know too much about their filament. But then there's also some cases where it looks like they can't help but know about the filament. So I think that's unanswered at present.
Oh, interesting, thanks. But while we're on the picture, where's the trapezium?
Oh, the trapezium is, so can you see my mouse cursor?
Yeah.
Yeah, trapezium's right there at the tip of my mouse. It's
got it.
It's where we don't have any protostars, not because they're not there, but because it's all saturated in the Spitzer bands that we can't really measure their spectral energy distributions, and so we can't tell if they're there or not.
Got it. Okay, cool, thanks.
John, I'm curious about the final system that you showed us, where the brightest source seemed to be off on the edge of the disk. What do you suppose is going on there?
Yeah, so it's this one.
Mm-hmm.
So yeah, so from the I should have put a plot of the kinematics as a backup slide, but the center of mass is sort of located like right here where my mouse cursor is, if you're able to see that.
Uh-huh.
Yeah, so the center of mass is right about there. That's where everything is rotating around that. And we didn't see any, at least in the molecular line data we had, which was C17O, which is a rarefied isotope of carbon monoxide. We didn't see any perturbation on the velocity field by this companion. So what we think is going on here is that this is basically a newborn clump that has formed in the outer disk, and so it's undergoing high mass accretion, and it just has a lot of material packed into about a 50 AU region, so it's very optically thick. And then these guys in the inner disk, they're smaller, and they probably have less mass, or they're more optically thick, and so they're not emitting as much. So I think it's the fact that this thing is big and there's a lot of mass associated with it right now, or a lot of dust mass anyway, that's causing it to glow so brightly relative to the other disk.
I see. Okay.
And a lot of the other disk structure has been broken up by the spiral, so we don't have like a smooth power law density profile going into the center.
Mm-hmm. Is it possible to estimate the I guess the infrared reddening or the absorption column as a function of position in this? I mean, with multiple wavelengths.
Oh yeah, I forget what the column density is towards this guy, but we measure a dust mass of about 0.1 solar masses towards this source, but it's got to be it's probably a lower limit due to the fact that it's optically thick, and then the dynamic mass it needs to be less than about 0.2 solar masses. Mm-hmm. But in terms of AV towards the center of the system, it's probably about AV of 50 to 100 at optical wavelengths towards the protostar itself.
Mm-hmm. Okay, thanks. So yeah. Are there any other questions? Okay, well, let's thank John, and thanks again for coming and giving us a great talk.
All right, thank you very much.
Hope you can visit in person at some point.
I hope so too. Have a good evening, everyone.